Okay, Matteo, whenever you want, you can start. I don't know if Maria is connecting or not, but...
Okay, so let me share my screen. Do you see it?
Yes.
Good. So yeah, I will start it now. So welcome everyone for this 7th and last talk for this year. Today again, me and Elena will explain something about finite element modeling this time. I will start with a brief introduction. So what is the finite element method and why do we use it in ophthalmology? So the finite element method is basically a numerical approach that is generally used to approximate the solution of partial differential equations. And it's used, it basically consists in subdividing a complex domain in simpler subdomains. So after this discretization, the infinite subdomains, the partial differential equations are approximated in each of these domains, and this is how the method converges to a solution. It's used generically in engineering to solve a wide range of problems like structural mechanics, diffusion problems, fluid dynamics, heat transfer, electromagnetic. As you can see here, this is a very easy example of a crash test of a car where finite element methods can help in localizing the concentration of stress and higher deformations. And in bioengineering as well, it is employed to analyze the stress-strain distributions of biological structures. Here you see a left ventricle during a cardiac cycle. So why do you use it in ophthalmology? Generically, in ophthalmology, finite element methods have been proven to be useful and to provide useful insights on physical phenomena that we would like to control, we would like to predict, but since we don't have a simple analytical solutions for them, we are not able to replicate them numerically. So it's been used to predict the outcome of surgeries. It's been employed also in planning of personalized treatments, as this nice work where they started from topographic data acquisitions, and they also used some experimental data to get a patient-specific simulation of a surgery. And it's also employed to replicate ex vivo experiments and to understand the stresses undergone by the samples during these experiments. So the eye is a very complex system, and numerical simulations are used to study it in different ways. So we can have structural simulation to study the eye. We can have computational fluid dynamic simulations that study the humors inside the eye and the pressure effect that these have on the surroundings, and also the fluid structure interaction between these two. And what I'm gonna present you now are generical aspects that apply mostly on all of these three different techniques. And I will give some examples mostly on structural mechanics because it's where I'm most focused on. And Elena later will explain more in details CFD and fluid structure interaction. So how does usually a finite element simulation work? We start from a physical phenomenon. In this case, I choose Goldman tonometry applanation as a simple example, which is simplified here. We have a tonometer, and the edge is applanating the cornea to measure the IOP. We model this phenomenon in a CAD model, and then we perform an analysis on this. And with analysis, I mean we give boundary conditions to the system, we apply some loads, we define the loads that our region of interest will undergo, and then we can reach a solution. And this solution will help us to analyze stress strains and deformation in the area of interest. So we have to pay attention to different aspects when performing such of a simulation. I try to summarize the most important ones, being the model construction, the definition of the boundary conditions, the meshing, and the material model we apply to our soft tissue. There are other aspects we have to be careful on when simulating, but these are the most important and relevant ones. So I already showed the eye, I already talked about its complexity as a system. When we want to model it, we will have different degrees of complexity. I will present now in order of ascending, increasing complexity from left to right, different ways to model the eye. Of course, the more complex the model will be, the more time consuming it will be. So it's always a matter of finding the right balance between how complex we want our model to be compared to how time consuming the simulation will be. For example, we can have analytical models of the eye that can be used to draw the model. And these, the literature is full of this, are based on average measurements based on healthy or not healthy people, or it can be patient specific. Of course, a patient specific model is more realistic. It comes usually from medical images. For sure, building the model in this case is more time consuming. When I talk about time efficiency, I mean either building the model itself and the time needed for the simulation to run after the model will be built. Also, I divided this modeling part into different classes based on the geometry the model will have. The model of the eye can usually be 2D, so bidimensional. In this case, I choose a 2D axis symmetric model, which means it's symmetric along this axis. So it means it's symmetric revolving around this axis. It's basically a slice of a 3D model, and we're just simulating one slice of it, symmetric revolving along this axis. And they can be 3D. Of course, 3D implies more detail, a degree of detail that is higher, but for sure it will imply way more efforts in modeling the system. And lastly, we can choose what do we want to model. We can choose to model a simple region of interest, or we can model the whole geometry. So not just what we want to really measure, but also the surrounding of it. Of course, when we model just the region of interest, we have to account for what is not model, is not present in the model with the boundary condition. And this we'll see a little bit better later. So we had these different approaches for modeling. The more complex, the more time consuming they will be. But what we really want to stress out in this point is that the complexity of the model really depends on what do we want to know. So it's not necessary to model the whole eye if we just want to study the epithelium of the cornea. And it's not even necessary that if a model is very complicated, this means it will be more accurate. It can be that a very complex model leads the same results of a less complex one, just in more time. So usually a common rule is starting with simple models and gradually increasing the level of complexity. So I spoke about boundary conditions. What are these boundary conditions? These are the constraints we set to our model that are necessary for this to have a solution, because we're dealing with partial differential equations. So partial differential equation systems, they have a solution only if they're constrained at the boundaries. We could speak a lot about boundary condition. I just choose one example on the cornea to more or less understand what we're talking about. The cornea I showed you before, it can be modeled in this way, but we have to account for the region of the corneal limbus joint. So how do we do this? We can either block, so set zero displacement to all the region in this joint area, or we can, this is another approach, have sliding boundary condition. This means we can allow for the cornea to slightly move along this direction, so along the direction of this edge. As I will briefly show you here, when I apply IOP, so I apply intraocular pressure to this cornea, they will deform in a different way. So as you can see, the cornea on the right deforms, it slides on these boundaries. So then what's the right boundary condition to assign? This is actually a very challenging process of the modeling process, because the right boundary conditions, they really change the output of the simulation, and choosing the right boundary condition determines how realistic your model will be. For example, I found this paper that deals with this cornea problem, and actually the authors here perform different simulation, just changing the angle of this edge here, of this corneal limbus edge. And they show that comparing the results with a whole eye model, which are most accurate, of course, because they really account for all the surroundings, just changing the angle will show how this result will be modified. And they found an optical angle at this point of 23 degrees, where the boundary condition applied this way lead to the similar results of the whole eye model. I also spoke about the mesh. So what's a mesh? When we apply finite element modeling, we discretize the domain in some subdomains that are called elements, and this is where we approximate the solution. So these subdomains are what creates the mesh of our model. There are many different types of elements we can look at. I will not go into the details of this. It's just they can be different depending on how many dimensions our model can have. We can have a 2D element, a 3D element. We can also have 2D elements in the 3D space, but it's not really worth to go into the details of this. What's for me is interesting is to go into the general aspects of the meshing part, which is another crucial process in the modeling. We see that when we have excessive distortion of some elements, we can have numerical errors. This means our mesh should be as regular as possible. Also, the higher the number of elements, the higher the accuracy of the model will be, but of course, the higher will be the computational time. So again, it's a matter to find the right compromise between the accuracy we want to reach and the time of the simulation. One thumb rule here is to have a higher density in the regions we actually want to investigate, and to have more coarse mesh in the rest of the model. And also, usually this leads to sensitivity analysis. So to performing an analysis that really tells us what's the minimum number of elements we need to reach the accuracy we're looking for. Also here I choose an example from the same paper as before. Here the authors were investigating the numbers of elements necessary to be modeled in the thickness of the cornea. They ran several simulations, always the same simulation, but with different numbers of elements in this thickness. I choose 5 in this image. They went from 1 to 8, and they showed clearly that the 1-layer simulation is not really converging to the same results as the 8 layers one, that is assumed to be the most accurate one. But they also showed that if they increase the elements from 2 to 6, the solution is not really more accurate. So the accuracy doesn't really increase after number 4. This means it will not be necessary to have 8 or 6 layers that will increase the computational cost, because we can reach the same accuracy with 4 or 5 layers of elements. So this means having a sensitivity and performing a sensitivity analysis. Last, I will go a little bit on the material properties. So in the FE solvers, we have different material properties implemented. So we have material models that define the response of the material when subjected to a stress. And as Benedetta already showed in her talk, the cornea has a very complex material response to stresses. So cornea is a biological tissue with fibers embedded in a collagen matrix. This means it has a hyperelastic response to stresses. So we can see in the stress strain curve, in the first part, we have an isotropic response, which is more linear. And then after a certain threshold of stress, we will have the fibers interacting So a more anisotropic response that has a more exponential behavior. And the most commonly used equation to model this behavior is this one, that I will not go into details because has been already explained by Benedetta. But what I really want to focus on here is that this equation relies on several parameters. And when we change the values of these parameters, we will actually change the response of the tissue. So how do we know which parameters have to be implemented in the solver? Because of course, changing these numbers will really change the solution. So the question here is, how do we really get to the right parameters in these simulations to actually go as close as possible to the reality? An option here given by FE is to optimize for these material parameters. So is to retrieve these parameters by comparing the numerical results we obtain from the simulation to some experimental results, and changing the parameter iteration by iteration in order to get the one that minimizes the optimization cost. So to be more clear, we start with initial values. We start the first simulation, which will yield to some numerical results. These numerical results will be then compared to some experimental results, and the difference between these two will define the cost. So the cost of this optimization. The idea is that the minimizer wants to minimize this cost. So as soon as this cost is not below a certain threshold, the minimizer will change the material parameters, so the input of this iterative process, and update it to have a new simulation and iterate the process until we get below our threshold. So we will get the optimal values that actually fit the experimental results we're looking for. And this means we can find through FE the experimental values that define a complex tissue, like, for example, the cornea. This is the last example I'm going to show you. There's a project we ran actually in our lab. We were interested about the stiffening process happening during the cross-linking. So in these two graphs that we are published in literature, you can find either a human and a porcine sample that were uniaxially tested before and after cross-linking. And as you can see, the cross-link curve is always more stiff, of course, than the untreated one. Our question was, how much stiff is this curve with respect to this one? So how do we model the cross-linking effect? So we used FE to recreate the same experimental setup they had in their paper, with two different samples geometries, two different fibrous orientation, human and porcine, modeling a uniaxial tensile test. And our idea was to minimize, to optimize, to get the stiffening factor induced by cross-linking. So I will not go into the detail of our optimization, but the idea is we were just running a simple model, a simple tensile test model. And what we managed to get, as you can see here, is that we found the optimal parameters that more or less match the experimental results. So the experimental curve are the one in red here for the human and the porcine corneas. And after cross-linking, you see our blue, no, actually the blue curve are the experimental one, and you can see the red curve, the numerical one, more or less fit the experimental data. Of course, it's not perfect fitting, but we were happy we found what we were looking for. So this is the first part of this presentation. I will leave Elena speaking about CFD and FSI more in detail.
Okay, thank you. Let me share the screen. And, okay, so thank you, Matteo, for the first part of the presentation. My work, as I presented last time, is focused on the non-contact tonometry of curves. So I will present some numerical simulations, and the example I will give you are focused on the curves, that is as I said, the non-contact tonometry, in which the deformation of the cornea is caused by an high velocity air jet. So we have two parts, a fluid part that is the air reaching the eye, and a structural part that is the eye. So to simulate the non-contact tonometry, some authors in literature used finite element modeling, simulating the air as a time-dependent pressure, so without modeling the fluid. But some other authors discovered that the geometry of the eye play an important role in the deformation of the eye during the air jet. So they performed firstly a computational fluid dynamic simulation in order to have the correct distribution of the pressure over the corneal surface, and then they used the output of this simulation to load the structure of the eye. But also in this case, we don't have the influence of the mechanical properties of the eye on the pressure. So the most complexity of the simulation is the fluid structure interaction simulation, in which the geometry and the mechanical properties of the eye influence the pressure over the cornea. So as Matteo just explained the finite element modeling, I will focus my part of the talk on computational fluid dynamics and FSI simulation. So CFD simulation is a numerical technique used to simulate and analyze the response of fluids, for example, gases and liquids. And this technique employs mathematical equations to solve the governing equation of the fluid. In particular, they solve equations of conservation of mass, conservation of momentum, and conservation of energy. Regarding the simulation of the air path, we need some requirements as an input of the simulation. First of all, we need a geometrical description of the phenomenon we are going to simulate. In this case, the phenomenon is the air that at a certain point reaches a velocity. So we need a very large domain in which this air jet can go through, and this domain should be large enough so that the boundary of the model does not influence what is happening inside. You can see here that the mesh of this fluid is different from the mesh of the structure. In particular, in CFD simulation, we can have structured or unstructured mesh. Unstructured mesh are the most used because they can fit each every geometry, and in the region of interest we have a finer mesh, while in the boundaries we can accept a larger mesh. In the boundaries of the region of interest, in this case in the boundary where the cornea and the eye should have been put, we used a structured mesh. This is called the boundary layer. In this layer we are more interested in the variables. So using a structured mesh, we can have a more accurate description of the variables in this region. So once, why we can have different mesh with respect to structural simulation? Because the method CFD uses to solve the equation is different. In particular, we are talking about the finite volume, not finite element as before, because in the structural solvers, the structural equations are written in a Lagrangian configuration. That means that the primary variable that in the structural simulation is the displacement varies with respect to the variation of the mesh. So the mesh is moving with the primary variable, while in the fluid equations the movement are very fast. We have very high movement. So an Eulerian configuration is used, so that means that the volume is fixed. We speak about control volume, and we see the variation of the primary variable, that in this case is the pressure or the velocity of the air, varying inside the control volume that is fixed. To explain better this concept, I can show you this video in which here you can see a structural simulation. You can see that the movement of the eye is related to the movement of the mesh. The contrary, the mesh is moving with the movement of the eye. Here you can see the fluid, and the fluid is moving inside the mesh that is fixed. So we look at the velocity of the air when the mesh is fixed, okay? So this is the reason why we need different meshes. So another input of the computational fluid dynamic analysis is to characterize well the fluid. So the fluid in this case is here, and we model it as an incompressible fluid with a specific density and dynamic viscosity. And in this case, the air is moving through a very small diameter cannula at a very high velocity. So the flow is turbulent, and we need to impose the turbulent behavior of the air. There are other cases in which the flow could be laminar, for example. Last, we have to impose the boundary conditions that are different from the structural simulations. We set them in terms of velocities and pressures. In particular, usually the velocity is the inlet of the system and the pressure the outlet. Okay, in this case, zero pressure means atmospheric pressure. So far from the region of interest, we have atmospheric pressure. Okay, so once we have these inputs that are the main inputs of the simulation, we can run it and obtain the results. For example, we have the results in terms of velocity field. This is the velocity of the air jet, but also distribution of the velocity field. You can see here with the streamlines that we can see the recirculation of the air if it is moving, where it is moving, okay? But also we can have the pressure field, that is the load. Before I said that in some papers was used to load the structural simulation. So with these quantities, we can work on the fluid variables, okay? So once we have finished the computational fluid dynamic introduction, we can go on the fluid structure interaction simulations that are a link between the CFD and FEM. Since I just explained the fluid part of my simulation, I'm starting from the structural part I have used for the fluid structure interaction simulation of the Corvis, and I've constructed a patient-specific corneal model starting from data from Pentacam. With the Zernick approximation of these surfaces, I've constructed the surface where we don't have data from clinics, and then this allows us to construct the patient-specific corneal model and properly meshed. You can see here a detail of the mesh, and in this case we used hexahedral mesh. The irregularity of the hexahedral mesh means that the faces of the hexahedron should be squared, and the angles should be approximately 90 degrees. Okay, then I will return to this concept, because these patient-specific cornea were then linked to limbus sclera of average dimensions to set the boundary condition of our problem, And in the simulation of the non-contact tonometry, it is important also to take into account the influence of the humors that are the liquid inside the eye responsible for the intraocular pressure. So there are a lot of techniques to model the humors, and it's possible to model them also in a Lagrangian way, so as a solid but with the characteristic of a fluid. And in this case, the problem of the mesh is evident because we have a semispherical geometry in which it is difficult to set an hexahedral mesh. You can see in the image of the left here inside the white circle that some elements are degenerated. That means that some sides are almost consecutives, some sides of the same elements. Here, a different technique has been used to mesh the geometry, and no elements are degenerated. So, as our rule is saying, this is the best mesh. But why? Because if we run the simulation, we obtain a concentration of stress that is non-natural. It's only numerical. And this is because the elements are degenerated and they deform in a way that is only numerical. Here instead, we can see that in these regions, we don't have this concentration of stress. So this is the reason why we should take a lot of care into the discretization of the structural mesh. Okay, so we talked about the structural model, the fluid model. Now we can speak about the interaction between them. In the fluid model, you can see that this velocity is the velocity of the curves that the device is providing us. Okay, so how does a simulation work? There are both the fluid solver and the solid solver work. First of all, the fluid solver starts solving the fluid dynamic equations, and the results of the fluid dynamic equations are the forces, in particular the pressure of the fluid. These pressures are given to the mechanical solver, which solves the solid mechanical equations that are the equations of linear elasticity. The results of these equations are the displacement of the solid part. These displacements are passed to the fluid solver, and then a convergence check is performed. If there is convergence, the simulation can go to the next increment. If not, they perform a loop in a way that they reach convergence both from a pressure point of view and by a displacement point of view. Okay. So here is just a slide to show you that the equations the different solvers are solving are different. But an important concept is that we have to force the coupling between the fluid solver and the structural solver so that they can interact each other. In particular, we should enforce the geometric, kinematic, and dynamic continuity. Geometric continuity means that the mesh of the solid part at the interface should be coincident with the mesh of the fluid part at the interface, so that the displacement of the nodes at the interface are the same, both from a fluid and from a structural point of view. Also, the kinematic continuity means that these nodes has the same velocities, and the dynamic means that we should have equilibrium of forces at the interface. So with this coupling, we are enforcing the fluid structure interaction analysis. So here I've put some softwares that are commercially available to solve fluid structure interaction simulations. In particular, I'm using LSDyna, but I know other people using other softwares, and I think there are some differences between them. For example, if the solution is solution of the solid part is implicit or explicit, but they do more or less the same. Okay. So let's go to the results of the simulation. You can see the synchronization between the fluid results and the structural results. So we can have results of both parts. Okay, you can see the velocity and the displacement of the cornea during the air puff. And in this way, we don't have to impose a specific pressure over the cornea, because we are simulating the process that is happening in clinics. Okay. Now I just want to show you an example of what Matteo was saying before, because I've spoken about the fluid structure interaction simulations, and as you can see here, we have a lot of results, and the complexity is very high. And well, if we are interested in the mechanical properties of the corneal tissue, they are perfect. But the computational cost is very high. You can see here 45 hours of simulation in 8 processors. And okay, it can be acceptable, but for a work, I was interested only in the air pressure without the mechanical properties. And so I decided to take this deformation during the fluid structure interaction simulation and to impose it as a moving boundary of a 3D CFD simulation without the structure. So the structure is not present, but I only have a movement of this boundary that replicates the same movement of the CFD, of the FSI. And I'm showing you that the results in terms of velocity and pressure, that are our variables of interest in this case, are the same, and the simulation lasts 13 hours. But then I wanted a faster simulation, so I tried with the 2D axisymmetric simulation. And with the same process, the same movement of the boundary, and with only one processor, it took 17 minutes with the same results. So we reach our take-home messages. The complexity of the model depends on the question we want to answer. So if we only are interested in the pressure over the eye, isn't necessary to simulate the whole structure of the eye, the crystalline lens, for example, and so on. So let's take care on the objective of the simulation. Okay. These simulations are useful to parameterize complex biological systems. And so, for example, in our case, we can isolate the influence of the intraocular pressure with respect to the influence of the mechanical properties of the eye. So this parameterization allows us to study some components of the eye and of the surgeries and the clinical tests that are present in clinics. And last but not least, computational simulations allow for patient-specific geometries and patient-specific analysis. And this is useful because if, for example, we are interested in knowing the mechanical properties of the cornea, they are different for each patient. So if we're able to perform a patient-specific analysis, we can better analyze the behavior or the pathologies of a specific patient. So this was all from our side, and I hope it has been interesting for you. And if you have any question, we are here. I don't know if Said is speaking because I saw its name lighting, but okay, you have a question. If you prefer to write it on the chat, it's okay for us because I'm not able to listen to you.
Now, do you hear me?
Yeah, okay,
Yes.
thank you.
Sorry.
Perfect.
Yeah. Thank you so much for your beautiful presentation, Matteo and Elena. Just I have a question. Assume that when we have a 3D model and in fact consists of cornea, limbus, xenolus, lens, and sclera. And we have in fact 6 parts. And when we import these parts into the CAE software like Abacus or something like that, we need to image them or in fact consider interaction between each other. Which one is better? And for meshing, actually, I know that it's more complex that because compatibility between meshes in some parts is very important. Do you know how we can solve this according to maybe your presentation in pages 20 and 21? Can you explain more about it, or?
I think it's my part of the presentation.
Yes.
Okay.
Yeah.
Let me share the screen. So that. Wow. Thanks. Okay. Are you referring to this part?
Yeah, 20 and 21, yeah.
Okay. I usually construct the model as all the parts have a direct interaction in terms of mesh. As you can see here, the cornea is linked to the limbus without any contact because there is continuity of mesh, both between the cornea, the limbus, and the sclera, and between the structures and the humors. So I impose the continuity of the mesh when I'm constructing them, when I'm meshing them. So I don't need any type of contact between the parts. That was your question, or it was different?
Yeah, it's okay. Yeah, I got it, and that was useful. Yeah, thanks.
Do you have any other question?
I see somebody writing. I don't.
Okay.
No, not anymore. Well, if we don't have any more questions, we can close it here, I would say.
Yeah.
Do you have any question from your side?
I don't.
I don't either. So thanks everyone. And this was the last talk, I think. So
we will see you all on the OBERON meeting in Antwerp.
And have a great day.
Yes.
Yes, see you.
Bye
Thank you very
bye.
much for the presentation. Bye.
Thank you. Bye.
Bye.
Thank you so much. Bye.